Okay, again, I'm doing these things in parts because I'm building things as I go along and probably forget. I wanted to answer that question about whether or not mutex is set to the signaled or to non-signaled state. And now see what I've done is I've introduced a whole blast of classes, okay? I mean, some of them I already had. And so I knew pretty much what was going on. And I wanted to make one of these, this here, a locked type object, okay? I already had a locked thing that used a critical section, so I decided I wanted one that used a mutex. Instead of just rewriting this and going back to using a separate signal, separate from the object. See, what I have here now is the object and the signal are one and the same thing, right? And the way it's set up is it auto releases itself. There's no, this line is gone. Anyway, now I couldn't test to see if it was set because it turns out that the thing that this is derived from is derived from something that derives privately from mutex. But I still wanted to know, so I just temporarily put it to public, and every now and again I wanted to print out to see if it's set. Now it turns out that I got a bunch of printouts saying it was set, but then eventually an assertion fired on a release, okay? And so what that tells me is that the method of checking to see if something is set here, where I've now isolated it into a separate class, is to do a weight 0. Okay? Now, a weight succeeds if a weight 0 returns set, returns a value of like self signal, which means object was acquired or whatever, right? Then the signal happens to be set. But you see that I guess would always be true in the case of a mutex. However, waiting on a mutex for any length of time acquires its ownership, right? So that means this test is not there's no const here really in this test as far as a mutex object goes, because that increments a count, the count of the number of owners of the mutex. I'm actually quite surprised that the program ran on for as long as it did, because these acquisitions none of them were being released, right? I was just many times they printed 4 or 5 of these before I got an assertion on a release call. I'm not really sure why that would happen on a release. It seems like I'm oversetting it, right? And then it should have ended up blocked. Like only one thread would have been able to get in to acquire it after the first call to this is set. However, No, I don't understand why it didn't lock up quickly. But definitely, just by logic, and of course we don't believe in logic anymore, but just by logic, the fact that we've called wait for single object, right, on a handle which is a mutex, means that we're supposed to call a release. And that certainly is not happening here, right? So this function is not valid for a mutex. So now the problem is disentangling that call, which is part of the base class for all these things, a signal class, okay, which had as one of its members was again the head top. Oh, the wrong file. H1. Okay, just before this not operator was that is set call. Okay, so anything that was a signal, you could check to see if its current state is set. Now it turns out that mutex had derived publicly from signal, so someone could have called that is set function. So one way, was to make this protected, and then I can make sure that nobody calls it, right? But the thing is, these are things you can get by. It's possible for someone to recast this, as a TS signal in some way, something derived from this, in particular the auto or the mutex lock class, it could call is set if it likes. So then what I did is I just defined an is set, or declared an is set function here, right, and not define it. So therefore, if anybody would attempt to try to call is set, then they get a linker error. But still, if you again, by recasting, it would be possible to get to the other is set. What I want is, I don't want this function to have anything to do with this class. I only want the bits of this class that have to do with the weighting and this thing, validation, copying, and that sort of thing, right? And that's okay. That part's fine. So what I did is, now all the rest of these types of signal objects can be tested safely. They don't need to be released for every acquire, right? You can just check to see if it's in a set signal to state or not. But this one requires a release. Right? This has a release function, but calling wait, while it might end up altering the state, calling wait 0, while it might end up altering the state of this object, there's no requirement to call release, right? That just might no, actually, you see, this release is a totally different thing. This release for this type of object is not something that you have to do after. You don't acquire a semaphore, right? A semaphore is a type of signaling object that has a count, okay? And what this release does is it releases a number of threads that are waiting on this particular object. Okay? So testing to see if this is in the signal state won't cause any waits to succeed. Right? It won't cause anything that's waiting on this to suddenly satisfy the wait. Well, I guess this thing could satisfy the wait, but no, that wouldn't happen actually. If you called it out of line, there's an ordering for this type of object, and if you're the last one on the list, you're not gonna acquire it. Not acquire, it's the wrong word, but you're not going to see it set. This here is a thing which can be set, right? And it immediately becomes unset as soon as it becomes set. Okay. So this is similar to that Intel instruction. Bit test reset, right? So it tests and resets in one step. And that's what this thing does. If it gets into a signal state and the wait, someone's waiting on it, and that wait succeeds, it becomes set for a second, it immediately, look at that. He's got I didn't write this code, in fact, but he's got his own, set, yes. Is set, right? To test to see if it is set is always going to return false. This MR means manual reset, which means that if this thing ever becomes set, it requires resetting, and this is resettable manual reset object, okay, which is a settable manual reset object. It's resettable, so it can be set and it can be reset, and and it's manual both ways. Okay, it doesn't do anything automatic. This one, that's kind of your basic type. You can set it like a Boolean on and on. In fact, look, this class derives from that. It's called a sync bool, synchronized Boolean. I'm not sure how well synchronized it is. So anyway, all I did then is I took the function out of the base class and call it, I don't know what name to give it. The whole purpose for this addition to TS signal is to allow you to test for the set or not set state of the object. So I call it a signal tester. This allows you to test the state. So a signal, I don't know what to call it, but anyway. So now that's completely gone from mutex. There's no way you're not allowed to check if it's set. You would have to release it. And these things are testable, so they derive from the tester, and then these start to derive from each other. And by this point, it's all gone. And also, like I said, I added this addition to the critical section locked, which was what it had before, and I tried that, and it worked fine with our program. And then I realized that I wasn't able to make that test I wanted to make. And now I know that not only can I not test that, but doing that test is a terrible thing. Okay, so that's one thing I found out. And well, I guess before I go, I'll show you what I've been up to on the other front, that is trying to look at these things, is I'm trying to make a little, well, I haven't really gotten very far with it. What I want to do is I want to make these various kinds of objects and somehow make a visual representation of them, like so I made a window, so therefore immediately I have to start adding functions to this class, and this class, and the window class, right? Because I got tired of typing bitlet and so on. But anyway, I was thinking that what I could do, see, it's called Bouncy Bouncy, is make some different colored balls or something, let's say, each one representing a different thread. Okay, so each one will have some data associated with it, and do something in its own thread. What I could do, or what I'd like to try to do, that sure looks like a nice blue. What I'd like to try to do, to illustrate the mutual exclusion idea, is to sort of draw a line here, okay? And in order to cross the line, a ball, imagine that these are balls, would have to acquire a mutex, okay? And what I could do is, let's say, add a little gravity or something and have the balls bounce around, and we'll see that we'll never get two things in that box. Or I could have them all stick to the thing, to the wall when they can't get in. They're waiting to continue, and we can see in which order they get stuck and then go in. And when one of them leaves, we should see another one enter, and so on. And that way we could visually see mutual exclusion occur. Or I could make another type of shape, like a circle shape or something, which has some mutual exclusion properties or something, right? I don't know. I'm thinking of something visual that would be interesting, because some of these other objects have some cool properties, like especially this semaphore thing. Oh, I forgot to colorize this. That thing that's like a counter. What you can do is you can have a whole bunch of things waiting on one semaphore, it's called, and then you can release a given number of them all at once in one shot using something called pulse event, right? So you could imagine a kind of cool thing that could in a visual way demonstrate how pulsing occurs, and then some things that immediately reset themselves, right? That could be represented by a color change, so it turns blue and then it turns back to red again or something. I'm just trying to make sure that I'm amusing myself while I'm doing this, and so I'd like to make it a little jazzy, things bouncing around the screens, little boxes that only one thing can go into. I think, well, with a semaphore, you can make the restriction a given number of objects. I lost the health. Every time I close that, I lose the health. I guess I'm talking about these things, so I wanted to get to talking about them. Semaphore. Wait for things. I've always got to find some weirdo way to get to where I want to go. Wait functions, synchronization functions. Where was I reading about Semaphore? It wouldn't have been here because it was the wrong color. Oh, pulse event is what I read it, which is something that's been phased out. Because it's unreliable for some technical reason. But anyway, it led me to reading about semaphores. And then there's this thing, you see, you can have something that waits on many threads, and one of the flags is that an object becomes set when all of the things it's waiting on, let's say threads, become released. Oh, that's what this does. Okay, I see. Yeah. So suppose we have a manual reset event object. Okay, so that's one of those ones that's just like a bool, and you have 30 threads waiting on it. Okay. Now, if you do this pulse event, all of the threads, what it's supposed to do, it won't work properly, but is release all of the threads that are waiting on that event, and then resets the object state to non-signal and then returns, you see. So this is a way of turning a manual reset event object into a type of auto reset object, right? And what does it do with an auto reset event? Sets it to non-signal and returns after releasing a single waiting thread. So if you've got 10 threads waiting on an auto reset event and you pulse it, that allows one thread through. So you can imagine too, visually, with that line I was thinking of, that box. It doesn't have to be a mutex line. It could be an auto reset. There could be an auto reset event being represented by that line, and you have all of the little balls sitting there waiting, and then call this pulse event and see one of them go in, and then pulse it again and see another one go in. And so we can see these things in action. There are all sorts of, as you can see, there are these ones that you can see here, New text you saw. Semaphore has to do with numbers, and I still didn't find it in the help. Where is this? Semaphore thing. Come on, where are you? Maybe there's something I create. Right. Okay. Now, what is a semaphore? See, it has a count, and it has a maximum count. In the state of a semaphore, a signal when its count is bigger than 0, and non-signal when it's 0. So, it's always signaled when it's basically it's a positive value when a count is non-zero, and then it's unset. Now the count is decreased by 1 whenever a wait function releases a thread that was waiting for the semaphore. So that means if you had 10 threads waiting on a semaphore whose count was 3, and one of them completes the wait, then the count becomes 2. So that, again, you can imagine the box and that line being a semaphore. So therefore, whatever the value of the semaphore initially is, should be the number of balls that would get past the line, right? No matter what the order is. Okay, there's a maximum value. All this name stuff has to do with making an object global. I mean, it can be global in the sense of see, there's global and local. When you have something that's named, okay, then another function or whatever can get a handle to that particular object by specifying the name. And if there's a global in front, then that handle becomes a system-wide handle. So like another process can access it. Now some of these things are used for what they call overlapped I/O, which is an important thing too that one should look at if you want to write efficient programs that aren't getting bogged down all the time. A lot of the reason why certain programs get bogged down and slow down and stop responding or just become sluggish is because I/O operations, it's not that they take up a lot of CPU, but that they have a higher priority than certain other things. And so if you have a bunch of threads in your program and one of them ends up in like a blocking state, input-output state, then the rest of the threads are going to run at a slow rate. And that was mentioned somewhere in here, that's why I'm mentioning it now. I wonder where that was. I copied down the comments. Where was that now? Probably in the file, because I want to do something about it. I think that I can. This is a good example of something that you can do. You can use that marshalling stuff for. Okay. User and fiber implementations are typically entirely in user space. Result of content, blah, blah, blah. Okay. Scheduling policy is in user space. Okay. So if everything is in what they call user space, right? Then what they call the scheduling policy, meaning that how you decide how much time to allow each thread to have per unit real time is easy to set up so that the program runs efficiently. However, let's say here, the use of blocking system calls in user threads. So that's just like reading a file, for instance, as opposed to kernel threads. So a user thread calling into the kernel a blocking call, right, is problematic because thread or fiber, because they block, and the other user threads and fibers in the process, they simply can't run until the system call returns. So it's just, the program just hangs, right? So if you're waiting on a named pipe read or something, right, and you're doing it in a blocking way, synchronously, your whole program just hangs, right? The user mode part of it hangs. That's the part that allows me to do these things, right? Like the other day when I had to terminate this program because I couldn't, I couldn't use the interface anymore, right? It was blocked in some kernel. This thing was blocked in some kernel call. Now, here, one of the solutions they say, if they offer, is to provide an I/O API that implements a synchronous interface. Now that's like the marshalling thing, by using non-blocking internally. See, well, that's where I put my comment. That's the marshalling thing. See, you make the call that's in one thread that's supposed to sit there and wait until the read completes, right? But it's not blocked in kernel 32.dll. It's just waiting for a non-blocking read to terminate. So it's just in a wait state, and a wait state is highly efficient. It costs no time at all to sit there and wait until one of these I/O things complete, right? Now these things come up, and whenever you're looking through the help file, you always see, whenever there's a read or something, I don't know, read file, okay, this LP overlap, okay, and everybody ignores this bit because it's complicated. Look at all this, I'd rather just say read file. But this overlapped I/O is non-blocking, and if you implement a read file function that works as though it were a blocking read, right? That is, it waits until things complete before returning. But a thread does that in a non-blocking way. Then you get the same functionality exactly, but you don't run into this problem of your program hanging because it's waiting for something to complete. It's waiting for what they call this get overlapped result. So if you can figure this stuff out, go through the help and try all the experiments and get it working, then your programs will not only run more efficiently, but you'll always be able to avoid the worst thing, which is a hang, right? Where it completely stops responding. Maybe that's okay if you're writing a computer game or something, but if it's a system in a bank or something, right? And it's in the middle of some kind of transaction involving millions of dollars, and the thing's hung, and you can't even click on it, then then you're in real trouble. I mean, you might as well start writing your letter of resignation for the next day. Anyway, this is probably enough for a video, so maybe I'll just upload what I've said now. And you know what I'm looking at doing. It's probably going to take a while to figure that out, to make it all cool and nifty with balls bouncing around. So, anyway, so I'll see you next time.